Welcome to Chapter 4, Hands-On, Screening in Python. 3 chapters of machinery deserve a machine. This one builds the smallest complete screening pipeline that still contains every logical move a real one makes. Define candidates, compute their intermediates, construct free energy diagrams, extract a performance number, rank, and check that ranking against the cheap descriptor model. It runs in NumPy, in under a second, on 5 catalysts that do not exist. Every adsorption energy here is an illustrative teaching value on a fictitious surface. Not a measurement, not a DFT result, and never to be attributed to a real material. 5 stages, each consuming what the last produced. Stage 1 defines the dataset and its descriptors. Stage 2 applies the scaling relation to predict the third intermediate and build all 4-step energies. Stage 3 draws cumulative free energy diagrams at 0 applied potential and at the equilibrium potential. Stage 4 extracts limiting potentials, overpotentials, and a ranking. Stage 5 places the candidates on the volcano. The point of Stage 5 is not to compute anything new. It asks whether a model using 1 number per catalyst reproduces exactly a calculation that used 4. If they agree, Chapter 3's collapse was real. 5 rows and 2 computed columns. The descriptors span 1.00 to 2.30 electron volts, straddling the apex at 1.60 that Chapter 3 derived. Catalysts A and B sit on the strong binding side, C just past the apex, D and E on the weak binding side. That spread is a deliberate act of dataset design. A screening set sampling only one leg would produce a monotonic-looking relationship, and someone reading the plot would conclude that stronger binding is always better. It is not. It is better only until the apex. 2 cheap sanity lines catch typos. Now the scaling relation earns its keep. We know the OH and adsorbed oxygen energies. We do not know the OOH energy, so rather than compute it, we predict it by adding 3.20 electron volts. The 4 steps follow as differences of cumulative energies, and every catalyst sums to 4.92. Look down the second and third step columns together, and the weld is visible to the naked eye. As step 2 climbs from 1.00 to 2.30, step 3 falls from 2.20 to 0.90, exactly compensating. Both welds hold. Steps 2 and 3 sum to 3.20 for every surface, and steps 1 and 4 sum to 4.92 minus 3.20, that is 1.72. 4 steps, 2 welded pairs, 2 free parameters. That is the entire design space. Now the asymmetry of the checks, which is the lesson. The sum check is guaranteed by how the 4th step was constructed, so it can only ever print true with deviation 0. It catches a transposed array, not a physics error. The meaningful check rebuilds the 4th step by a different algebraic path and compares. Plot cumulative free energy against reaction progress. Start at 0 for the clean surface, add each step in turn. At 0 applied potential, every profile is a rising staircase, and all 5 end at the same place, 4.92 electron volts, because the overall reaction does not care which surface catalyzed it. The catalysts differ entirely in how they distribute that climb, which is another way of stating the design problem. The largest uphill step already separates them. For A and B, it is the 3rd step. For C, D, and E, it is the 2nd. Those are the 2 legs of the volcano, appearing as 2 bottlenecks. Apply a potential, and every electron already transferred lowers the level, tilting the whole staircase uniformly, 1 tread at a time. At 1.23 volts, every profile ends at exactly 0 to 0 floating point error. That is the sum rule seen from the electrochemical side, and it is a genuine test of indexing arithmetic that is easy to get off by 1. Catalyst A's adsorbed oxygen level, at minus 0.86, is the deepest well in the table, a pit the reaction must climb out of. Catalyst E is the only one whose first step is still uphill. Nobody is fully downhill. Now compress each diagram into one number. The limiting potential is the largest step energy expressed as a potential, and the overpotential is that minus 1.23. The ranking is C at 0.420 volts, then B at 0.570, D at 0.670, A at 0.970, and E at 1.070. C wins not because it binds oxygen strongly or weakly, but evenly. Its welded steps are nearly equal, so it sits just 0.050 volts above the floor. Stage 5 maps each descriptor onto the Chapter 3 volcane and compares element by element. The shortcut and the long calculation agree to about 2 times 10 to the minus 16 volts, and the two rankings are identical lists. A model knowing only one difference of adsorption energies reproduced a calculation that used 3 adsorption energies and 4 step energies. Under these assumptions, the rest was genuinely redundant. The agreement was not automatic. Steps 1 and 4 are invisible to the descriptor, and the printed margins, between 0.65 and 1.08, show how far they were from mattering. Compute that margin in any real screening. This pipeline is complete in its logic and hollow in its inputs. A real one replaces teaching values with slab calculations, where the choices of facet, termination, and coverage often move the result more than the functional does. It carries error bars, and here the conclusion is uncomfortable. The uncertainty is comparable to the differences being ranked, so the defensible output is not that C is best, but that C, B, and D are indistinguishable, while A and E are clearly worse. It adds stability filters, which eliminate more candidates than activity does, and it must eventually add kinetics, which this framework never modeled. Let us recap. We ran a 5-stage pipeline on 5 fictitious catalysts with illustrative adsorption energies. The scaling relation predicted the third intermediate and built 4 steps, exhibiting both welds, 3.20 and 1.72, with 0 deviation. Profiles at the equilibrium potential all ended at exactly 0, with 2 distinct bottlenecks. The ranking was C, B, D, A, E, and C sat just 0.050 volts above the floor because it split the welded pair nearly evenly. The descriptor alone reproduced that ranking exactly. Next, ML screening and the limits of CHE.